we had started our discussion by considering a particle in a three-dimensional spherically symmetric potential, and we saw that, so the Hamiltonian for that 3D spherically symmetric potential, and the Hamiltonian for a particle moving in this we had worked out, and we had also worked out the Schrodinger equation. So let me write down the Schrodinger equation for a particle moving in such a potential. So the Schrodinger equation is minus h cross square by 2m del square psi plus v, which is just a function of the distance psi, is equal to E psi. So this was the Schrodinger equation we were trying to solve. And we saw that how it naturally led us to the angular momentum operator, because when we wrote this in a spherical polar coordinate system, then the Laplacian operator broke up into two parts, a radial part and a part which had derivatives with respect to theta and phi. The radial part we saw could be associated, so this whole thing over here, this differential operator, we saw could be written as, could be associated as follows. There was the radial momentum squared plus the angular momentum squared by r squared So if we went into a spherical polar coordinate system, or even where the motion could be broken up into two parts, one was the circular motion, the angular motion, the other was the radial motion, the Hamiltonian could be written in this form, or which you could say that if you wrote the Laplacian in a spherical polar coordinate system, the radial derivatives you could associate with the radial momentum, and the angular derivatives in this Laplacian you could identify with this term over here, the angular momentum squared by r squared. Then we proceeded by looking at, by breaking up this wave function into a product psi, which is a function of r theta and phi, into a product of a function of r and the spherical harmonics y Lm, which were functions of theta and phi. And when L squared, this doesn't act on this, the function of theta and phi, and when L square acted on this function of theta and y on the spherical harmonics, it gave us L into L plus 1 h cross square. So we are going to be left with an equation for Fr, and that equation, if I put in the operators corresponding to this, which is nothing but the radial part of the Laplacian operator, what that gives us is 1 by 2m 1 by r square del by del r square del by del r, this operator acting on F. This will have a, I can put a minus h cross square over here. So this is what comes from the radial momentum, or you may say it comes from the radial part of this Laplacian operator. L square, when it acts on this, gives us plus h cross square L plus 1 F. This is equal to, this plus Vf is equal to Ef. So the the angular part of this Schrodinger equation has already been solved, and that can be cancelled out throughout, and we are left with this equation which governs the radial part of the Schrodinger equation. Note that when I had written this earlier, there was a mistake in these derivatives. you should correct it, and this is the correct expression to use. So we now want to solve this, which is the radial part of the Schrodinger equation. The angular part has already been solved when we have solved the angular momentum operator. Okay. Now we can simplify this equation somewhat by defining another function which is denoted by gr, and this is defined as follows, that gr by r is equal to fr. So fr is the radial part of the wave function and gr is r times the radial part of the wave function. So plugging this into the radial part of the Schrodinger equation, we have to first calculate d by dr of fr, which gives us d by dr of g into 1 by r plus rather minus 1 by r square into g. Then we have to use this to calculate 1 by r square d by dr r square into d by dr of f. This is the term which appears in the radial part of the Schrodinger equation, and written in terms of g, what this gives us is 1 by r square d by dr, and here we have r into dg dr minus g. And if we differentiate this, we find that when the derivative acts on this term, it gives us 1 by r d square g dr square. When the derivative acts on r, it exactly cancels out the term which I get when the derivative acts on this. So this is all that we have left. So let us use this in the Schrodinger equation. So now the Schrodinger equation, the radial part of the Schrodinger equation becomes 1 by 2m. I can take the h cross square outside also, h cross square by 2m, and then I have 1 by r d square g dr square plus L into L plus 1 into gr by r plus Vr gr by r is equal to E gr by r. Getting rid of these extra factors of 1 by r throughout, this whole thing can be written as follows. So what we have is minus h cross square by 2m plus, so the potential plus h cross square by 2m into L plus 1 by, there should be a 1 by r square here which I have forgotten to write, because there should be a 1 by r square here also, because we have L square by r square. Okay. So it is the angular momentum squared by r square which appears in the Hamiltonian, so there should be a 1 by r square here, and the 1 by r square comes here also, and finally we have a 1 by r square term over here. Now let us look at this equation a little carefully and try to understand what we have obtained. We had set out to solve a 3-dimensional problem. The 3-dimensional problem, we solved the angular part separately. So it reduced to a single equation for the radial part of the wave function. Then we made some substitution and we finally obtained this equation. Now if you look at this equation, it is a 1-dimensional equation and it looks like a 1-dimensional Schrodinger equation for a particle which is moving, which is there in a 1-dimensional potential, which is just a function of r. Okay, because a particle in a 1-dimensional potential, the kinetic energy will be p square by 2m, which is the derivative squared by 2m into minus h cross square. Then we have this extra potential. So the original 3-dimensional particle is moving in this potential Vr, but the Schrodinger equation for the r part of the wave function has this extra potential over here. This is equal to E. So this is equivalent, the 3-dimensional problem is equivalent to a particle in moving in 1 dimension in a potential which is somewhat different from the original potential. The potential has this extra term over here, and you might be able to easily identify what this extra term is. This extra term is nothing but represents the centrifugal force which appears in classical mechanics. If a particle is going around in a circular, the L over here quantifies the angular momentum. So if you think of it classically, it tells you that the particle is going around, and when a particle is going around, you can associate a fictitious force, the centrifugal force, and this is how it comes into this 1-dimensional potential. So you have this extra potential coming here, which you can think of as arising from the centrifugal force. So now you have a 1-dimensional potential problem which we have dealt with in quite detail earlier on in this course. R is restricted to being greater than or equal to 0. So you can think of the potential being infinite for negative r, and it has this value for positive r. Okay. So the 3-dimensional problem gets reduced to this 1-dimensional potential problem. So this is the first simplification which can be made. Okay. Now we are going to focus particularly on the hydrogen atom problem, where the nature of the potential we know is 1 by r. Okay. But before going to that, let us just consider some generic feature. So let us assume for the time being that this potential is attractive. So if I just draw the potential over here, this is r, this is v, this is the effective v, not v. So if I just first draw this potential over here, let us assume that the potential is attractive. So it is something like this, and it goes to 0 at infinity. So the potential dies away at infinity. So it will be something which is negative, and it is some attractive potential. This is the potential which was there in 3 dimensions and which appears here also. Now there is this extra potential over here which behaves as 1 by r squared, but which is positive. And this potential increases if L is larger. So this potential I can draw over here. It is like this. If this potential which we are originally given, if it falls off slower than 1 by r squared, for example a 1 by r potential, then at small r this potential, this part of the contribution from the centrifugal potential is going to dominate, whereas at large r this one is going to dominate. So the resultant potential, which is the sum of both of these, in which the 1-dimensional particle moves, that will look something like this. So it will be dominated by the centrifugal term, this term over here at small r, and it will be dominated by the actual potential at large r, In between there will be a transition where it will go over from this to this, and there will be this region over here where the potential will have a will have a transition from the negative to a positive value. Now we are interested in particles which have negative energy, which correspond to bound states. So we are considering E less than 0, which correspond to bound states. E greater than 0 corresponds to a particle which comes from infinity and gets scattered and goes away. So we are not dealing with scattering problems, we are dealing with problems where the particle has an energy less than the energy of the potential, less than 0. So the energy of the particle will be something like this. So classically, if I had a particle which had energy E in such a potential in one dimension, the classical motion of the particle would be that it would oscillate between these 2 points. And there is one equilibrium point over here which you can easily calculate, where the kinetic energy and the potential energy, this whole potential, are equal. Now classically, what does that correspond to? Classically, if the particle has the energy here, so if the particle has this energy over here, the radius of the particle will remain at rest here as far as the r motion is concerned. So this corresponds to circular orbits, because the r remains fixed, the particle has got some angular momentum, so this is a circular orbit. When the energy, the equilibrium position corresponds to circular orbit, because the radius doesn't change, it remains fixed here. The particle has some angular momentum, so it keeps on going around at that fixed radius. So this corresponds to a circular orbit. This is a circular orbit, which is the equilibrium point, and you can easily find out where the circular where at what value of the radius this is going to be by just differentiating this whole potential and setting it equal to 0. You also have other possibilities if the energy is more than that. So the other possibilities, the radius keeps on changing between these 2 values. So these, in the central potential, you know what these orbits are. These are going to be the elliptical orbits, where the radius is going to vary between 2 values. So when the energy is more than this, more than the equilibrium value, the minimum value which you can have, then you are going to have elliptical orbits. So classically these correspond to elliptical orbits for a 1 by r potential, for a central potential which is 1 by r. For any other potential, you will have some arbitrary kind of orbit which will not be elliptical, some arbitrary figure which may not be closed. But in one case, if you think of it as these are all going to be planar orbits. So in one case it is going to be a circular orbit, in the other case it is going to be some complicated orbit, okay. But there is going to be one radius r1 and a radius r2, between which the orbit is going to vary, and you can find out where these radius r1 and r2 are. So it is going to be some complicated orbit, okay. In general it may not close, so it may just be something like this. For a 1 by r potential, we know, for a Coulomb or a gravitational potential, we know that the orbits are closed and they are circular orbits. So in general, for a non-zero value of L, let me again, the potential is some potential like this, and we know some approximate methods. In some cases the problem can be solved exactly. If the problem cannot be solved exactly, then we can use the WKB approximation to find out some approximate solutions in such a potential, and I will not go into that again because we have already done it. We have already dealt with the one-dimensional situation, so I shall not be dealing with that here. I shall consider only one particular case over here, which is the 1 by r or the Coulomb potential with the application to the hydrogen atom. So for the hydrogen atom, this is the particular case which we are going to consider. For the hydrogen atom, V of r is equal to 1 by 4 pi epsilon naught into E square 1 by r with a minus sign, because the potential is negative, it is attractive, the two charges are opposite. E is the electronic or the proton charge, 4 pi epsilon naught we all know what it is, and 1 by r is the distance. So, this is the Coulomb potential acting between in the hydrogen atom case. But before we go on to this discussion of the Schrodinger equation of this equation for the hydrogen atom, there is another complication which has to dealt with. So, let me first deal with that and get over with that and then come back to this. So, the hydrogen atom we all know is actually a two body problem, it is not a one body problem, because a hydrogen atom has got a proton, there is a proton and there is an electron, and this is the hydrogen atom. It is not a one body problem. The problem we have been dealing with till now is a one body problem where there is a particle moving in a given potential. Here there are two particles which are interacting with each other through a potential. So, the problem is somewhat different. But this problem can be reduced to the problem we have been dealing with. You might have already studied it in your classical mechanics course. Let me just go through it over here, let me just go through the steps over here how it can be reduced to a one body problem. So, let us choose some coordinate systems. So, we are going to use this particular set of coordinate systems to start with, and let R1 or let R does not matter, R1 be the position of the proton, let R2 be the position of the electron. So, the Schrodinger equation which we have, the Hamiltonian, let us just bother about the Hamiltonian, which is a classical quantity. Okay. So, the Hamiltonian which we have now, the classical Hamiltonian is a function of the momentum of this particle and the momentum of this particle and the potential between these two. So, this is a function of P, the P of the P1, let us label the proton by 1. So, P1 squared, there could be two particles of two arbitrary mass, does not matter, by 2 m1, this is the kinetic energy of the first particle, plus P2 squared by 2 m2, this is the kinetic energy of the second particle, and then we have the interaction which is minus E square by 4 pi epsilon naught, then we have the mod of R1 minus R2. This is the distance between, this is the Coulomb attraction. So, the Coulomb attraction, the potential depends on only the distance between these two particles. Now, it is convenient, instead of using this coordinates, this set of coordinates, it is convenient to introduce some different coordinates. These different coordinates are the center of mass position r, so this is the center of mass. So, this will be m1 r1 plus m2 r2 by m1 plus m2. Instead of using the two r1, two vectors r1 and r2 as the coordinates, we are introducing a different coordinate system. The coordinates we are going to choose are the position of the center of mass and the vector which is the difference of these two vectors, which is r1 minus r2. You can very easily see that this is as good a coordinate system, set of coordinates, as r1 and r2, because you can easily eliminate this capital R and small r and write it, get r1 and r2 out of it by just some algebraic transformations. So, given r1, r2 you can get capital R and small r, or given capital R and small r you can get r1, r2. So, they are equivalent, there is just some algebraic relation between these. So, we can do our whole analysis with this. This is the first thing. So these are our new coordinates. If we write the Hamiltonian in terms of the momenta corresponding to these coordinates, the method of doing that you might be already knowing. You write down the Lagrangian for this system in terms of these new coordinates. Once you have the Lagrangian, you can easily calculate the momenta, you can easily calculate the Hamiltonian. This is something which you must have done in classical mechanics. I will just write down the result. So if in terms of these coordinates, you work out the momenta corresponding, you write the Lagrangian in terms of these coordinates, and then you work out the momenta corresponding to these coordinates, and you can also work out the Hamiltonian in terms of the corresponding momenta and these coordinates. So now the Hamiltonian will have two parts. There will be the Hamiltonian, let us write it as capital P, of the center of mass, which I can write as 2 capital M, where M is the combined mass of the whole system. So there is not this is still the classical thing. So this is capital P squared by 2M. This is the Hamiltonian, the kinetic energy of the center of mass, plus there is another part to the Hamiltonian, which is the small p, I can write it as small p, by 2 mu, and we still have the same potential, which is E square by 4 pi epsilon naught into R. The potential now depends only on R, which is the difference between these two positions. So P is the momentum conjugate to this R, which is, you might say that P is the momentum corresponding to the separation, this relative motion between these two particles, and capital P is the momentum corresponding to the overall motion of the center of mass. So the motion has been decoupled into two parts. One is the overall motion of the center of mass, this is the center of mass which is moving, plus the relative motion of these two particles. So the Hamiltonian now also has two terms, the kinetic energy. One is the overall motion of the center of mass, and this is the relative motion of the two particles, the momentum corresponding to that. So this involves derivatives. So if I write it as an operator H, my wave function will be a function of capital R as well as small r, and this is equal to E psi. Now what is my Hamiltonian operator? This involves derivatives only with respect to capital R, the motion of the center of mass. This involves derivatives only with respect to the small r, the relative motion between the two particles, and this is a function of small r alone. So I can write down my Schrodinger equation now. My Schrodinger equation is minus h cross square by 2m, and then I have a Laplacian del square with respect to capital R, and I have acting on psi, and I have another term which is minus h cross square by 2m this should be 2 capital M, and this should be mu, where I have to still define what is mu. So mu is the effective mass, the reduced mass, which is 1 by m1 plus 1 by m2. So 1 by mu is equal to 1 by m1 plus 1 by m2. So mu is the reduced mass. So mu has contribution largely from the smaller mass, because for the smaller mass the 1 by that ratio is going to be larger. If one of the m's is very large and one of it is very small, it is the one which is small which is going to contribute largely to mu. And for a system with a proton and electron, the major contribution to mu comes from the mass of the electron. So mu, the value of the reduced mass, is closer to the electron mass than to the proton mass. But it will be different, for example, if I have a deuterium atom, where instead of a proton I have a combination of proton and neutron. So if I have a deuterium atom, the reduced mass is going to be different. Okay, so you should bear that in mind. So I am now writing down the Schrodinger equation. So let me just write it clearly over here. So I have minus h cross square by 2 capital M del square r acting on psi minus h cross square by 2 mu del square small r acting on psi plus v, which is a function of small r alone acting on psi, is equal to E psi. Now this wave function psi, I can use the method of separation of variables again. So the wave function psi, which is a function of capital R and small r, this I can break up into two parts. So one will be psi, let us say m, which is a function of capital R, and we have psi mu, which is a function of small r. So if we plug this into this equation, so using this separation of variables into this equation, this product form in this equation, let us simplify this. So the first Laplacian will act only on the part of the wave function which involves capital R. So what that gives me is minus h cross square by 2m. So what I am going to do is a familiar operation. Let me just tell you straight away. I am going to put this into this, and then I am going to divide throughout by the whole thing. Okay. So this is what I am going to do. So the first term gives me minus h cross square by 2 capital M, and I have 1 by psi capital M del square r psi capital M. So this is all a function of capital R. This is equal to E minus V, and I have plus h cross square by 2 mu, then I have del square small r psi mu divided by psi mu. So I have just taken some terms onto the right hand side, put in the product form for the wave function, and then divided by the wave function. And this is what I get. Now the left hand side, you may see, depends only on capital R. The right hand side depends only on small r. So the resultant of this whole thing must be some constant, and let us call this constant E1, or let us call it ECM, center of mass. So we have now got broken up the whole thing into two set of equations. The first equation, let me write down, the first equation is minus h cross square by 2m del square capital R psi capital M capital R is equal to E center of mass into psi capital M R. So this is the first equation. This, you can see, is an equation which is quite familiar to us. It represents the motion of a free particle. So the center of mass behaves like a free particle with mass, the combined mass of the two particles. And we know that the solution of this equation are just plane waves. So the motion of the center of mass is not something which is unfamiliar. It is just moving like a free particle, so it can have any value of momentum, and you can superpose wave functions with different value of momentum and obtain this. So we can straight away write down the wave function for this. This will be equal to e to the power some coefficient, let us say a1, e to the power I p dot capital R plus B1 e to the power minus I capital P dot capital R, where P, capital P, is equal to square root of 2me by h cross square ECM. Here I can put a Cm also, center of mass. So the this is P, center of mass. So the center of mass behaves like a free particle which can move with a particular momentum in some direction, and you can construct states by superposing wave functions with different values of momenta, and the center of mass motion is decoupled from the rest of the motion. So let us now look at the relative motion between these two particles. That is the one which is of greater interest. So that equation now becomes minus h cross square by 2 mu del square small r psi mu small r plus V r psi mu small r is equal to E minus EM ECM psi mu smaller. So we see that the relative separation between the two particles, that the Schrodinger equation for that is exactly the same as the Schrodinger equation for a particle in some external potential, just that the energy is the total energy of the combined system minus the energy of the motion of the center of mass. So if you have these two particles and the total energy is some value, you have to remove the part which goes into the kinetic energy of the center of mass, and the rest of the energy is in the relative motion of these two particles. So we see that this the two body problem has been reduced to a set of one body problems. One of them is free, we did not bother about it. The other one body problem corresponds to a particle of mass, a particle of mass mu moving in the same Coulomb potential with energy which is equal to the total energy minus the kinetic energy of the center of mass. Now we are free to choose any inertial frame which we want. So we can always choose an inertial frame where we are in the center of mass of the hydrogen atom and do the whole thing. So we, in general, we are not interested in the translational kinetic energy of the hydrogen atom. We are interested in the internal energy levels of the hydrogen atom. So for most of the analysis, we can forget that the hydrogen atom has got some translational degree of freedom also, that the whole atom can move with some kinetic energy, and we shall, when we talk about the energy levels of the hydrogen atom, we usually refer to the possible values of energy, values this energy can have, that is the total energy minus the translation energy or the internal energy of the hydrogen atom. So from now on, when we refer to the energy of the hydrogen atom, we shall actually be referring to this, and when we refer to the mass, we shall be referring to the reduced mass, and the potential is unaffected. So having shown this, we can go back to our original problem, which is the problem of a particle moving in a central potential, and we can easily see that the hydrogen atom can be mapped onto such a problem. It is exactly the same, just that the mass is the reduced mass and the energy is the internal energy of the hydrogen atom. So let us come back to this equation which we were trying to solve. Okay. So we are going to look at a special case where the potential is 1 by r. So let us first try to qualitatively understand certain features of the solution based on whatever we have already learnt. So let us first consider the case when L is equal to 0, the particle has no angular momentum. There are various possibilities, right? L can take any integer value, L can be 0, 1, 2, 3, 4, etc. So let us first consider the case when L is equal to 0. When L is equal to 0, the centrifugal part of the potential does not operate, so the resultant potential is just the Coulomb potential. So let me draw the potential first. So the potential will look some like this. It falls off as 1 by r. So at large distances it goes off, it disappears, it goes to 0, and at small distances it blows up, and at r equal to 0 it blows up to minus infinity. So this is the potential V of r. Now let us consider a particular value of the energy. So this is E. Now from our analysis of the one-dimensional problem, what have we learned? We know that classically the region accessible to the particle is over here to the left. This is the classical region, and over here classically you would not expect the particle to be found over here. So we know that the wave function will die down exponentially to the right hand side. We know that in the classically forbidden region the wave function should die away exponentially. It will have some exponential kind of behavior on the right hand side. Now asymptotically, as you go to r equal tending to infinity, the wave function, the potential itself will disappears. So at large r you can just think of the wave function satisfying this equation. At r tending to infinity, the wave function will satisfy this equation. This will be equal to minus 2m by h cross square E into G, and E is negative. So this whole coefficient over here is some is some positive number because E is less than 0. So G of x, G of r will have two parts. It will be some a e to the power rho x and plus b e to the power minus rho x, rho r, and we want the function to disappear at large r because it cannot, it has to disappear, otherwise it will blow up. It will not, the total integral will not converge. So we see that this term has to be 0, and G of r will behave as e to the power minus rho r. So this is the behavior on the right hand side beyond the classical point. In addition, the wave function also has to disappear at the origin because the potential jumps to infinity on the left hand side. the wave function has to disappear here. So the wave function should disappear here, should disappear at the origin also. So based on this now we can work out what the wave function looks like. So the lowest energy state, for all cases the wave function has to start from 0. So let me just plot what the wave function will look like. For the lowest energy state, the wave function starts from 0 and then it will fall off. In this place it has to be exponentially falling. So for certain value of energy E, the wave function which starts from 0 comes here and then it will match continuously and go to 0. For other values of E, you will not have such a continuous matching. When you match over here, you will find that you may pick up some growing part also, and those values will be ruled out. So you will find that there is a certain value of E where the wave function starts from 0 and then continuously smoothly goes over to this exponentially decaying part at large r. This is the lowest energy state. The first excited state will again start from 0. So it will be something like this. It will have one 0 crossing and then go over to infinity, go to 0 at infinity, fall off exponentially. The second excited state will have two 0 crossings, third excited state will have three 0 crossings, etc. So this is the behavior of the L equal to 0 wave function, qualitative behavior. Now let us also look at the qualitative behavior of the wave function when L is greater than 0. There the potential behaves exactly the same as in the earlier case at large r, but at small r it again blows up. So the potential now looks like this. It does not go to infinity, it blows up as 1 by r squared. So if L is greater than 0, the potential blows up at near the origin. In addition, and at large r it behaves just as the case when L is equal to 0. So if this is the value of the energy, then we can make a guess as to what the ground state wave function will now look like. The ground state wave function will look something like this. It will be some oscillating kind of function here in this region. These are now it has two classical turning points. One is here and one is here. So it will die down beyond these two classical turning points. It will go to 0 at this point. In between it may have some oscillating, it will have some oscillating kind of exponential. Here it will have some decaying exponential. So we can guess the ground state will look something like this. It will go up and then it will decay off exponentially here and it will go to 0 over here. The first excited state will again start from 0 and then it may have one 0 crossing and then it will die away exponentially, and the second excited state will have two 0 crossings. But the key difference, if you notice, is that in the situation where L is equal to 0, the wave function was more concentrated towards the origin, whereas in this case the wave function is largely restricted in this region over here, and the probability of finding the particle near the origin is much lower. So for the L greater than 0 cases, the peak of the wave function, or the probability of finding the particle, the region where the probability of finding the particle is maximum, shifts away from the origin, and for larger and larger values of L it goes further and further out. Because if you increase the value of L, this potential will start rising faster. So this whole thing will shift to the right, and the place where the probability of finding the particle is maximum will also shift to the right. This you can interpret somewhat classically also. Classically, the zero angular momentum state corresponds to a particle which goes through the center, oscillates back and forth through the center. Classically, if the angular momentum is 0, then if this is the center, the particle motion is going to be like this. because the angular momentum is 0. If L is greater than 0, then obviously the particle cannot go to the center. The particle will move in some orbit, some trajectory, some elliptical trajectory away, elliptical or circular trajectory away from the center. So, you see even classically you will find the particle at the center only when the angular momentum is 0, and if the angular momentum is greater than 0, then you will never find the particle at the center. This is also reflected in the quantum situation, where the wave function moves further and further away from the origin as you keep on increasing the value of L. We shall look at the exact solution to the problem in the next class. I will stop here for today.